And if you actually look at this, I looked into a little more detail, and if you remember, I discussed local minima. So you can ask, are these local minima? Well, these are sort of local minima, but actually they're this is a case where you have a plot of the goodness of fit, actually, if this is minimizing, it's the badness of fit. And these minima here are widely separated. These are drastically different solutions, 3 and 1 versus 2 and 2. And they're actually, these goodnesses are essentially the same. Namely, the average distance between the point and the cluster is essentially 1.5 for both solutions. And depending on exactly the random numbers in the cluster generation and the starting point, you're going to find different solutions. So these solutions are so clear that the Gaussian distribution within the clusters is going to affect the answer. So you will even get this ambiguity even if you run 20 iterations. And if you actually calculate mathematically what the 2 cluster versus the 1 v3, you will find, let's take the case where those clusters have 0 radius. So in the case of 0 radius, and I do 2 and 2, the center is going to be halfway between the center of each of the 2 clusters is halfway between the centers of the generated clusters. So that's going to be, as those cluster centers are always distance 3 apart, that says this goodness of fit is 1.5. Let's check that back here. It's 1.501 for this case here, so that's not a bad. That obviously the spreading of these Gaussian clusters is going to change the magic value of 1.5. And if you, on the other hand, if you actually look at the mathematics of point-size clusters with the one center at the center of one of the clusters, let's put it at the origin, the 0, 0, that's one of the centers of the clusters, then you'll find that sort of cluster center which minimizes which represents 3 clusters, it has a goodness that you can find out is 1.47. This is exact for small clusters. So these average distances are almost the same. And in fact, a non-intuitive solution with 3 and 1 is actually likely to be the best solution for cases of very small clusters. And when you have the larger clusters, these numbers are going to be smeared on a case-by-case basis. You can't tell what the answer is. Probably you'll get more often than not, it will be this one. But these are so close, it's going to be very difficult to tell them apart. So that's why I suggested changing the goodness, the quality judgment to not the mean, but the maximum distance. And if you look at maximum distance of points to clusters, you will find that the 2 and 2 case still has a maximum value of 1.5 because all distances are 1.5, whereas the 3 and 1 case has 1 cluster where the distance is 0 and 3 clusters where the distance is greater, and they average to this 1.47 because that's the 0 plus these other 2 distances. And if you look at the maximum distance, actually the root 5, namely for this center here, 2 of the clusters are distance root 5 from the center, 1 of the clusters distance root 2, and that gives you this 1.47. But there are 2 clusters which are root 5 which are full of 250 points, which are root 5 from the actual determined cluster center, and so the maximum is root 5. So you expect, if you change that criteria to be maximum, to always get the solution which is 2 and 2, which is the intuitive solution. It just points out that naive choices of in these heuristics you can get, if you're not careful, you can get funny answers. And this is a very important point about all these functions. There's a hill between the solutions. And There are actually multiple solutions. I pointed out there's symmetry-related solutions, and there are a total of 6 possible solutions here with almost the same goodness, and they're all stable on small perturbations and need big changes to get from one to another. And this fact that you have to do big changes to get out of a minima is a very important feature in the real world. I mean, if you look at things like which operating system is important for smartphones, currently you have a balance between iOS and Android with those roughly equal, with a certain amount of BlackBerry and a rather small Windows 8. Even if BlackBerry and Windows 8 are better, which we don't want to discuss, that's not important for this lecture, the fact that iOS and Android are sitting there with a lot of market share is very hard to dislodge because that's a stable situation. You have to do something drastic. You have to come up with a major change to get out of these minima. Another example, I think, is VHS. There was an example of various video formats, and the format that actually probably wasn't best is the one that ended up winning because people were familiar with it and the other solution wasn't able to take over. The next few slides just show funny examples where you run probably a game with iterations of one. I just picked out clearly non-optimal solutions. Here's an example for 2 clusters on the large case, and we can see that this cluster here has got half of this, or maybe a third of this one up here, and this cluster here has all of this, and 2/3 of that cluster. So that's a pretty messy case. So almost certainly a local minimum. Here's another example here where this cluster, we're trying to do 4 clusters, and we get these 2 joined together. This one is bled over here, and this neat compact cluster is actually chopped into 2. Those are actually good clusters, but it would be better to use this cluster to split this into 2 to get a better, an optimal solution. So this is again a local minima, but not a global minima. Here's again 4 clusters for the large case, and we managed to join these 2 together and split this one into 2. So you can see what these local minima are. They're actually not too bad. It's what you'd get actually if you ran more clusters. You would often split this one into 2. But it is very unlikely that it's better to split this one into 2 than put 1 cluster here and 1 cluster here. Here's actually one that's almost right, but somehow this center bled over and stole some points from up here. Here's a k=4 small clustering. We managed to split this cluster and join these 2 clusters together. What do we have here? Well, here we have 2 clusters with the very large case, and instead of joining clusters in pairs, we've done some rather messy thing with this cluster bled over here, and we have 2 2/3 of a cluster over here. So here's a k=6. Well, we're not certain this is a wrong case, but it's different from what you might expect. Normally, we would expect to split these larger clusters. Here we take one of the smaller clusters and split it into 3. That's a pretty example, again showing the importance of k-means has in defining geometrically nice regions, which are all co-located points. Here's k=8. We split this one into 3, this one into 3, and these are perfectly beautiful single cluster solutions. This is pointing out again, these are all local minima. The fact that this cluster is just 1 cluster, we know that's going to make it locally very stable. And these 3 here are actually pretty stable. Once you decide there's 3 clusters over here, and maybe the initial conditions implied that, then you're likely, if you happen to generate in our random choice of clusters, most of our clusters are centers over here, and maybe we got trapped in a solution with 3 there.